All right, welcome to section 10.1.5, which is going to be conditional probability. And we'll get started. The probability of an event under the condition that some preceding event has occurred is called conditional probability. So we already know something happened. It is represented by the symbol P for probability, parentheses A is an event, this bar means given, and then B is another event. So this is read probability of A given B. Again, that vertical bar means given. The way we find conditional probability, again, we use that symbol, probability of A given B, is the probability of A and B together is in our numerator, and our denominator is the probability of the bottom, which is probability just B. The way I remember it is this kind of looks like a fraction. So whatever is on the right-hand side is the denominator, and then the top is the two together. So it says Miss Jones works in a medical research lab where the drug that promotes hair growth in balding men is being tested. The results of the preliminary tests are shown in the table. So what I like to do is first kind of total things up. So it says using the drug, I'm going to total this up. So that would be 2,400. So 2,400 total people are using the drug. And then 1,600 are using the placebo. And if you don't know, placebo is they're given some sort of drug that's like a sugar pill or something. So they mentally think they're taking a drug, but they're actually not. So they're seeing if it's just a mental game. If we look at hair growth, add across, we have 2,800 that did have hair growth, and then 1,200 that did not have hair growth. And if we look over here to get our totals, if I add straight down, I get 4,000, or if I add straight across, I get 4,000. So 4,000 total people were in this. So here it says, what is the probability that a test subject's hair grew given he used the experimental drug? So I'd have probability of growth given drug. So our numerator is probability of growth and using the drug. So that's 1,600. Our denominator is just the probability of them using the drug. So 2,400 people used the drug. So we're doing 1,600 out of 2,400, which is going to be reduced to 2/3 or 0.666. So 66.6% of the people that took the drug saw their hair grow. For the second one, it says, what's the probability that a test subject's hair grew given he did not receive the drug? So we're looking for the probability of growth given no drug. So growth and no drug, or the placebo, was 1,200. And just the people that used the placebo were 1,600. So again, we're limiting our total. Our total is not actually 4,000 because we're assuming in the first one we knew they were using the drug, so our total is 2,400. Second one, we know they're just using the placebo, so it's out of 1,600. This is going to reduce to 3/4 or 0.75. So that means that 75% of the people who did not receive the drug or received the placebo saw growth. So something might be wrong with that drug because we're seeing more growth from the no drug than the drug. For the next one, Alex is conducting a survey of families with 2 children. If the family is selected at random, what is the probability that the family will have exactly 2 boys if the second child is a boy? So this is kind of a given. So we're really kind of looking at probability of 2 boys given a second child, second is a boy. So what we're going to do is make a list. And on all of our lists, the boy is going to be in the second slot. So we could have boy as the first, boy as the second, boy as the third. We could have boy as the first, boy as the second, and then a girl. And then again, the boy, we're given that the second one's a boy. So we're putting boy in the second. So I could have a girl, a boy, and then a girl, and then a girl, a boy, and a boy. So that limits our denominator now. So once we know the boy is the second child, that we only have 4 total possible outcomes, and we want exactly 2 boys. So that doesn't work. This one would work because there's 2 boys. This one does not work, and this one has 2 boys exactly. So we'd be saying 2 out of 4 or 1/2. For number 3, a 12-sided dodecahedron has the numerals 1 through 12 on its faces. The die is rolled once, and the number on the top face is recorded. What's the probability that the number is a multiple of 4 given that it's an even number? So we're looking at our probability here. So probability of multiple of 4 given even. So on the die itself, there are 12 numbers, 1 through 12, but if we think about how many are even, half of those are even. So we're limiting that down to 6 now. And so we have to think how many of those are multiples of 4. So if we write all of our even numbers out, 2, 4, 6, 8, and 12, 10 and 12, sorry. 1, 2, 3, 4, 5, 6. That's how we get to 6. Well, 4 is a multiple of 4, 8 is a multiple of 4, and 12 is a multiple of 4. So 3 out of those 6 are true. So our probability is 1/2. Again, since we knew it was even, our denominator is now 6 because there's only 6 even numbers. For number 4, a box contains 3 blue marbles, 5 red marbles, and 4 white marbles. If one marble is drawn at random, find the probability of blue given not white. All right, so I'm going to first figure out the total. So I have 3 blue, 5 red, 4 white. So that's 12 total. All right, so probability blue given not white. So we know for the A, it wasn't white. So that left us with 8 other possibilities. So for this one, we have 8 as our denominator. And so we want to know probability blue out of that. So again, out of these 8 that we have remaining, there are 3 that are blue. So this would be 3/8. All right, for the next one, it says probability not red given not blue. So if we're looking at probability of not blue, there are 3 that are not blue, meaning 9 are going to be not blue. And so then from there, again, we know that it was not blue. Which of those are not red? So 4. So 4 out of 9. So again, all these conditional probabilities is we're limiting our total from what the total originally was. We're also going to look at the next page at the very bottom. You are going to do these problems 5 through 8 on your own, but we're going to do number 9 together. So it says you survey a group of juniors and seniors. The diagram relates students' class and whether a student is employed after school. Find each probability. Let J, S, E, and U represent junior, senior, employed, unemployed. All right, so here it says 52% are juniors, 48 are seniors. Of those juniors, 35 are employed, 65 are unemployed. For seniors, 55% are employed, 45% are unemployed. And remember, when we have a tree diagram like this, you multiply from branch to branch. So first thing we're looking at is I'm going to multiply from branch to branch to find these end results. So a junior that's employed is 0.182. A junior that's unemployed, if I multiply 0.52 times 0.65, I get 3.38. So out of all the juniors and seniors, the juniors that are employed make up 0.18 or 18.2% of all those juniors and seniors together. Juniors that are unemployed make up 33.8% of the junior and senior class. And then 0.82 times 0.55 is 0.264. So 26% of all the juniors and seniors combined are seniors that are employed. And then if I have a senior that's unemployed, 0.48 times 0.45 is 0.216. So 21.6% of the seniors, sorry, 21.6% of all the juniors and seniors are seniors that are unemployed. So find the probability that a student is employed. Well, I'm looking at these end results of employment and I add them together. So I'd be doing 0.338 plus 0.216. And that gives me 0.446. So 44.6% of all the juniors and seniors together are employed. So this one says probability of a senior given employed. So our denominator is going to be, we know that they're employed. So this 0.446 is going to be in our denominator because that's the probability of them being employed. And then senior and employed is going to be our numerator. So senior employed is right here, 0.264. So we're going to be doing 0.264 divided by 0.446. So that would be 50.5919 or 59%. So if we know someone's employed, then 59% of the employed students are seniors, is basically what we're looking at. If we just looked at the employed students in the junior and senior class, 59% of them are seniors. For the next one, we're looking at a junior given unemployed. So the next thing I have to do is find the unemployed. So the probability of unemployed is going to be 0.338 plus 0.216. And that's 0.554. So that's our denominator for letter C. That's the probability of being unemployed. And then junior and unemployed is our numerator, which is 0.338. And we get 0.610. So if we look at all the unemployed juniors and seniors, 61% of those would be juniors. Probability of senior and unemployed. So then, again, we're looking at unemployed, 0.554. Senior unemployed is 0.261. Or sorry, 0.216. And that would be 0.3899 or 39%. So 39% of the unemployed students are going to be seniors. And if we notice, if I add 39 and 61, I get 100, which should make up the 100 because 100% of these unemployed are either juniors or seniors. And the last one, probability of a junior given employed. So again, now our denominator is the employed. So that's the 0.446. And junior employed would be 0.182. And when I divide that out, I get 0.408. So 40.8% of the employed students out of the juniors and seniors are juniors. All right, so you're going to try these classwork problems on your own. Try your best. If you have questions, let me know.